This video is part of the MCAT Chemistry video course. Subscribe and hit the bell if you'd like notifications about the release of new videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to go over enthalpy, and first we'll cover exothermic and endothermic reactions, and then we'll finish by talking about Hess's law. We're going to talk a lot about enthalpy in this video, so it's really important that you understand what that is. Enthalpy is basically the energy that's contained within the bonds of molecules. And it's not exactly that simple, but you're totally fine thinking about it like that, especially for this test. Understanding the concept of enthalpy will be really helpful whenever you're trying to figure out if a reaction is releasing energy or absorbing energy. And that's a really common thing that they test on the MCAT. There are two extremely important things you have to have understood, and that is breaking bonds will require energy. So you're going to have to put in energy in order to break a bond. And intuitively, I would just think about this as breaking pretty much anything else. If you tear a piece of paper or you break a pencil, all of that requires energy, and bonds are no different. The other thing that's really important is that forming bonds releases energy. And the way I would think about this is you've put in a bunch of energy to break bonds, and you're left with kind of a disorganized bunch of atoms that aren't really connected in any particular way. And so that would be a really unstable state because the atoms want to connect to create more stable molecules. So when they form these new bonds, they're creating these stable molecules. And anytime that you go from unstable to stable, there's going to be a release of energy. So breaking bonds requires energy, and it creates a pretty unstable situation with the atoms, and then forming bonds releases energy because we're taking that unstable situation and then creating a bunch of more stable molecules. If you compare the situation to magnets, I think it becomes a little easier to intuitively understand. And just think about you had a bunch of magnets that were stuck together, and then you put in the energy to take the magnets apart, and then all you did was kind of throw the magnets on the floor together, and the attraction between the magnets caused them to snap together. And so that would be the forming of bonds. And when the magnets were in the process of snapping together, they're moving faster, so they're creating more kinetic energy due to that attraction. If the intuitive understanding is a struggle for you, I wouldn't worry too much about it. If you just have these two facts memorized, that breaking requires energy and forming bonds releases energy, you're going to be totally fine. Now we'll look at exothermic and endothermic reactions. These graphs are showing us the change in enthalpy that's happening to the reactants as they form the products in whatever chemical reaction is taking place. In order to change reactants into products, you have to start with breaking bonds. So if we look at the first part of our curve, we start with reactants, and then the enthalpy increases because we're inputting energy to break those bonds. And we do that until we hit what's called the transition state. The transition state is an intermediate type of compound that's in between reactants and products. The amount of energy that's required to reach the transition state is called the activation energy. Once that transition state is reached, all those bonds of the reactants are broken, and they're going to reform new bonds that's going to give us our products. So it required energy to go from reactants to transition state, but then when we go from transition state down to products, we are releasing that much energy because now we are forming new bonds. So the overall change in energy would be how much energy did we release minus how much energy did we have to put in. And that would be from, if you drew a line at your reactants and then drew a line about where your products would be, that would be your change in enthalpy, which we write as delta H. So notice how in this one, when we formed our products, we lost more energy than we had to put in to reach that transition state. So overall, our products have a lower enthalpy than our reactants had. So the molecules themselves had a negative delta H because they lost some of that enthalpy that was contained within their bonds. Now you need to think about where did that enthalpy go, or where did that energy go? And where it goes is just to the surroundings. So imagine that you did this reaction in a solution that's in a beaker. The molecules themselves are losing the energy, but the surrounding water that's containing the reaction is absorbing that energy. So now that water is getting hotter. So anytime that your molecules have a negative delta H enthalpy during a reaction, your surroundings are going to get hotter because they're gaining energy. So the surroundings gain energy and their temperature goes up, so they have a positive delta T. Anytime this happens, we would call that reaction exothermic. On the right side, we want to break this down the exact same way, but this one is going to be an endothermic reaction. So to reach the transition state, that is still the activation energy, and we are breaking bonds, so that is requiring an energy input. And then when the transition state reforms the products, that would be a release of energy because we're forming bonds. But for this one, notice how the amount of energy that we had to put in to get to the transition state is far greater than the amount of energy that was released whenever we formed the products from the transition state. So to find the total delta H, you draw your line at the reactants, draw a line that's close to where the products would be, and now that is the delta H, but this time we were moving up, so we have a positive delta H. So when the reactants formed the products, the molecules gained energy, so there's a positive delta H, and then you have to ask yourself, where did that energy come from? It would have to come from the surroundings. So the surroundings lost energy, and this would cause a decrease in temperature, so negative delta T. We're going to work our way towards Hess's law, which is a way to calculate the change in enthalpy that happens during a reaction, but first we need to go over a couple terms. The first one is the standard state. The standard state of an element is the form that the element takes under a given set of conditions. We have a list of elements here: carbon, hydrogen, chlorine, nitrogen, and oxygen. And when we create the standard conditions, these elements are going to take a particular form. And so for carbon, it forms solid carbon. Hydrogen forms H2 gas. So for hydrogen, there's actually two hydrogen atoms that are connected to each other in the standard state. And then the exact same thing happens for chlorine, nitrogen, and oxygen. Those are all what we would call diatomic gases. But the standard state can be applied to any element, and it's just what form does that element take under these specific conditions. And you don't need to worry at all about what those conditions are. Just understand this concept of what the standard state is. We then use the standard state as a reference point whenever we're trying to calculate heats of dissociation and formation, which we're going to go over right now. The heat of formation tells you how much energy is released whenever you form a new molecule in your reactants, where the atoms or the elements that are in that molecule, but in their standard states. For example, we'll look at the formation of water first. So the two atoms that are in water, or the two elements, are hydrogen and oxygen. So that means that our reactants would have to be those two things in their standard states. So we have hydrogen gas and oxygen gas, and you want to think about this exactly how we just went over in the previous part of this video, where we're starting with our reactants, which would be H2 gas and O2 gas. We are putting in energy to break those bonds, and then there's energy being released whenever new bonds are formed to make the product, which is H2O in this case. So what this number over on the right is giving you is the change in energy when we go from reactants to our products. So it's the delta H of forming water from hydrogen and oxygen. Notice how it is kilojoules per mole, so it is only the energy that is released when we form 1 mole of water. So right now our equation shows us that we have 2 moles of water. What they're normally going to do is make your product have just 1 mole, so we're only forming 1 mole of H2O, and then they're going to change your coefficients to fractions. So they'll actually do like 1/2 of O2 because we only required 1 oxygen, so it'd only take half of an O2 to give us that 1 oxygen. Below that, we have another example, which is the heat of formation for ammonia. And notice again how we used our weird coefficients that have fractions in them. So for example, for NH3, you would only need 1.5 H2s to get 3 hydrogens. For 1 nitrogen, you would only need half of an N2 to get 1 nitrogen. Now we'll go over the heat of dissociation. And the heat of dissociation is the exact opposite of the heat of formation. The heat of dissociation looks at how much energy is required to take the elements that are in a molecule and turn them back into their standard states. So if you look at our example down here, it's the exact opposite of what we have on the left. So we're going from water to the elements in their standard state. And the heat of dissociation is going to be the exact same magnitude as the heat of formation, but the opposite sign. So you're basically just working exactly backwards on your curve. So the reactants for the heat of dissociation of water, the reactants this time would be H2O, and then the products would be H2 plus O2. The amount of energy that would be required to break the bonds in water is exactly equal to the amount of energy that was released whenever we formed water on the first graph. So to get from water to the transition state, is the exact same amount of energy that is released when we go from the transition state to water. And then the same thing is true if you look on the left side. The amount of energy required to break the bonds that are in H2O2 is equal, if you look on the right side, to the amount of energy that's released when the transition state forms H2 and O2. So overall, your delta H on the right side will be the same magnitude, but the opposite sign of the delta H on the left side. And that's going to be true for the heat of formation for any molecule. So if you look at the heat of formation for the ammonia, the heat of dissociation is the exact same magnitude, but just a different sign. And you can think your way through these two graphs on the bottom to kind of reason out why that is true. And the reasoning is not as important as just understanding that that's true for the test. Although if you understand the reasoning, you will be able to work your way through more of these types of problems. Now we can finally go over Hess's law. And Hess's law combines those heats of formation and dissociation for the products and the reactants in a reaction and allows us to calculate the total change in enthalpy for an entire reaction. So here we have a list of molecules and their heats of formation. Notice how on the left side we have the elements in their standard state, and on the right side of those reactions we have the molecule, and then we are given the amount of energy that's released when this happens. The way you want to think about the reaction below is that we're taking our reactants, we are breaking their bonds, and then forming those standard states, and then we're taking those standard states and forming these new products. And that's not what's actually happening in a reaction. So in a reaction, we don't always form the standard states, but you can think about it like this whenever you're trying to logic your way through how we use the heats of formation and dissociation. So on the left side, we have our reactants. So for the left side, we're breaking those bonds. So we're going to use the heat of dissociation for the molecules on the left side. So look at CH4, and CH4 has a heat of formation of negative 74.8. So the heat of dissociation would be positive 74.8, and I'm going to round that to 75. O2 is not listed because O2 is the standard state. So if we take O2 and then we form O2, we are going to have a change of enthalpy of 0. So anytime something's in its standard state, the heat of formation is 0. Now for the products. The products are the bonds that are forming. So now we want to use the heat of formation for these. So we're going to use the values that are given to us, and we're not going to change the sign. So CO2 is negative 393.5. I'm going to round that to negative 400. Next, for H2O, the heat of formation is negative 285. I'm going to round that to negative 300. And that may be too large of a round. It really just kind of depends on what your question is and what the answer options are. So you can start with the easier round where you do a very large round and get an easy number to work with, like negative 300. And then if that doesn't work out, you can do a smaller rounding and use maybe something like negative 280 or negative 290. It's all very dependent on the type of math that your problem is going to need and the answer options. Now for the negative 300, there are 2 moles of H2O being formed. So we need to put a 2 in front of that negative 300. So we want to combine our total values here. So basically just an addition. So we do 75 plus negative 400 and negative 600. So the total change in enthalpy for this reaction would be negative 1000 plus 75, which comes out to be negative 925, and that is kilojoules. So overall, what we found was that the delta H for this reaction was equal to the heat of dissociation of the reactants plus the heat of formation for the products. So you can follow this equation that we have written, and you just want to be really attentive to the values that they give you and make sure you're clear on if they gave you the heat of formation or the heat of dissociation, so that way you can flip the sign whenever it's needed. Sometimes you'll see Hess's law written different ways, where it will be the heat of formation of the products minus the heat of formation of the reactants. This is literally the exact same thing as the equation above. They're just doing it without changing one of the heats of formation to the heats of dissociation. So you will get the exact same value. I don't know why the first equation isn't the way that it's usually presented. In fact, it's usually this bottom one where you're using the heats of formation of products and reactants, but they mean the exact same thing.